In this video, we're going to essentially expand our ability to handle indeterminate forms. Well, first of all, we have to recognize that there are other indeterminate forms out there, not just 0 over 0 or infinity over infinity, and then also recognizing these other forms and then figuring out ways of evaluating them, right? So we're essentially going to be looking at more I don't necessarily want to say complex limits, although some of them are more complicated than the ones that we've dealt with thus far. Others, it just takes a keen eye to be able to rewrite them, and then we'll be able to evaluate them using any of the techniques that we've used up to this point, including our new rule, L'Hopital's rule, right? So let me just kind of go through case by case and do maybe a couple examples of each. There are indeterminate forms that look like this, where you have the product of two functions and one function approaches 0 and the other function approaches infinity. So you have this 0 times infinity form, where on the surface you would say, man, well, 0 times anything should be equal to 0. But that statement is true only if you're multiplying 0 by a specific number. Here, you're not multiplying a specific number. What you have here, essentially, is you have the product of two functions, right? And the 0 here is basically saying that this function is getting arbitrarily small. Right? That's what the 0 is saying. You have one factor that's getting smaller and smaller and smaller. And then the infinity, you'd have another factor that's getting arbitrarily large. Right? So what happens when you multiply them? What happens when you multiply something that is getting very, very small by something that's getting very, very large? We don't know. And the reason we don't know is because a lot of it has to do with the rate at which this thing is getting smaller and the rate at which this thing is getting large, right? So we can't just look at this and say, oh, this is going to be 0, or this is going to be 1, or this is going to be infinity. We can't tell. That's why it's called an indeterminate form. We can't tell just by looking. All right. So let's look at a few simple examples of this case. Right. And the goal here is to use algebra, right? The goal here is to use algebra to convert this product into a fraction where it's either of the form 0 over 0 or infinity over infinity, right? That will be the goal, right? In fact, in general, that's going to be the goal in all the cases that we look at in this video. All the examples that we're going to do, we're going to find some trick from algebra, right, and or trig that will allow us to rewrite these other indeterminate forms to convert them to the more familiar, right? Even though we don't like them, we're more familiar with the 0 over 0 and the infinity over infinity. All right, so let's take a look at a few examples from this. So let's take a look at the limit as x approaches 0 of the cosecant of 6x times the sine of 7x. Right? And so here's our product, right? Let's take a look at the limit of each of these separately to see what happens, right? So let's take the limit as x approaches 0 of the cosecant of 6x, right? Well, one of the things that we are more familiar with or more comfortable with as far as the trig functions are concerned is that it's easier for us to work if they're in terms of sine and cosine as opposed to cosecant and secant. So let's rewrite this. Cosecant is 1 over sine. So this is the limit as x approaches 0 of 1 over the sine of 6x. Well, as x approaches 0, the sine function approaches 0. So we end up having 1 over 0. And we know that's our infinite limit form. So this fraction approaches infinity, right? So that's what happens to this factor. So as x gets very, very small, cosecant of 6x gets very, very large. Well, what happens to the other factor as x approaches 0 of the sine of 7x? Well, we know that the sine of 0 is 0. So as x gets very, very small, right, the sine of 7x approaches the sine of 0, which is 0. So this factor is getting arbitrarily large. And when we say arbitrarily, we mean it can be as large as you want. There is no limit, right? There's no bound on how big this can be. And similarly, this factor is getting arbitrarily small. It's getting as small as this can possibly be. So we do have the form infinity times 0, right? And as much as we would like to say that infinity times 0 is going to be it's something that we know without doing any work, we don't know, right? So how do we evaluate this? Well, the trick that we used over here to figure out that this was in fact an infinite limit is the same trick that we can use to rewrite this whole thing. So just by using our definition of our basically our reciprocal identities from trig, if I take the reciprocal of cosecant of 6x, then in the denominator I will have the sine of 6x, and in the numerator I'll be left with the sine of 7x. And now, again, based on what we just did over here, this numerator approaches 0. This denominator approaches 0. So we do have an indeterminate form where we can now apply L'Hopital's rule. So if we take if we apply L'Hopital's, and remember what L'Hopital says, take the derivative of the numerator. The derivative of the sine of 7x is 7 cosine of 7x because of the chain rule. And similarly, the derivative of the sine of 6x is 6 cosine of 6x, again because of the chain rule. And now, as x gets very, very small, the cosine of 7x and the cosine of 6x, they both approach 1. So it's no longer an indeterminate form. So let me write this as 7 times the cosine of 0 over 6 times the cosine of 0. So that's 7 times 1 over 6 times 1. So this limit, which again started out giving us some crazy expression that we didn't know what to make of this, by using what we know about trig, using our new technique, L'Hopital's rule, we're able to evaluate it, and we get that this limit is 7/6, right? All right, so let's try another one similar to this. Now, what tends to happen in a lot of these like 0 times infinity forms, you end up having a lot of trig functions. So if you're not comfortable with trigs, trig functions, I will definitely say, have like your trig formulas handy, have the unit circle handy, because if you mess up recognizing or evaluating the trig functions, then that's a problem. All right, let's take a look at this one. We have pi over 2 minus x times the secant of x. So again, we have a product. Let's take the limit of these two functions separately to see what actual form this limit takes on. So we have the limit as x approaches pi over 2 from the left, and the first factor is pi over 2 minus x. Well, here, when we plug pi over 2 in for x, we'll have pi over 2 minus something that's very, very close to pi over 2, but smaller, so that difference is going to be 0, right? What about the other one? Well, if we have the limit as x approaches pi over 2 minus, well, this is our secant function. And again, as I said, if you're more comfortable, and I think most of us are more comfortable thinking in terms of sine and cosine, not necessarily secant, cosecant, rewrite secant as 1 over cosine. Now what happens here? Well, x is approaching pi over 2 from the left. That means you're just a little bit less than pi over 2, but really, really close. That means you're in the first quadrant. In the first quadrant, cosine is positive. But as you approach pi over 2, cosine approaches 0. So it's of this form. It's our infinite limit form, 1 over 0 plus. So this is now positive infinity. So we do have the same kind of, in this case, 0 times infinity form. How do we turn this into like 0 over 0? Well, do the same thing we did there. Rewrite secant, right? Rewrite secant as 1 over cosine, right? So just do a little bit of trig / algebra up front. So that means the linear function here, pi over 2 minus x, that stays in the numerator. So pi over 2 minus x. And then when I take the reciprocal of secant, the cosine now goes in the denominator. And lo and behold, when I evaluate the top separately, I will get 0. That's right here. And we saw it if we evaluate just the bottom part. So the bottom approaches 0. So this is of the form 0 over 0. So now I can apply it L'Hopital's. Take the derivative of the top. So when I take the derivative of the top, I'm left with a -1. And then the derivative of the bottom is sine. Right? And then this I can evaluate because this as x approaches pi over 2 from the left, the sine approaches 1. It approaches positive 1. So what do we end up here is -1 over 1. So that's -1. Again, not necessarily what you would try to if you try to assign a value of this and say this is always going to be a certain number, it hardly ever comes out to be whatever you think it is, right? In fact, sometimes it could be 0, or sometimes it could be infinity. It could be any real number or plus or minus infinity. That's why we call it indeterminate. It's not something that we can identify simply by looking. There has to be a process by which we can evaluate this, right? And our process now involves using possibly a lot of algebra, a lot of trig, in addition to this new rule, L'Hopital's rule. All right? Now, there's another form. So second one of our bullets. You have a form that looks like this. Infinity minus infinity, right? So what happens here is that you end up having a difference between two functions. And now both functions are getting arbitrarily large, but you're subtracting, right? So both functions are getting arbitrarily large, right? And then you're taking the difference. But because they're both getting arbitrarily large, you don't really know how that difference is going to play out. Is the if they're getting large at roughly the same rate, then yeah, the difference will be roughly the same. But what if this function, your f of x, is getting larger at a much faster rate than g of x? Or conversely, or not conversely, but the flip of it, what if g of x is getting larger at a much faster rate? Then it's hard to tell what's going to happen to the difference, right? And again, it's not something that we can tell by looking. So this infinity minus infinity is another one of the indeterminate forms. And again, what we're going to be using is algebra / trig to try to rewrite these in such a way that we can use one of our techniques. It doesn't always end up being L'Hopital's rule. It can be L'Hopital's rule, but it might just be something previously that because we did a whole set of techniques as far as limits are concerned. All right, let's look at some examples of the infinity minus infinity case. So let's say we have the limit as x approaches 0 plus, and what we have is the cotangent of x minus 1 over x, right? Well, let's look at both of these separately. Well, I think we can clearly see that if we take the limit as x approaches 0 plus of 1 over x, well, that's as clear as it can be as far as an infinite limit, right? So positive infinity. So this one goes off to positive infinity. What about the cotangent? Well, let's see. So we have the limit as x approaches 0 plus. So the cotangent, that is 1 over tangent. So I'm going to rewrite that. So this is 1 over tangent. And the thing is, as x approaches 0 plus, which would tell me that we're in our first quadrant, but very, very close to the positive horizontal axis. So as our x gets very, very small, but from the positive side, the tangent also gets very, very small, also from the positive side. So this is, again, 1 over 0 plus, which is positive infinity. So again, these are both infinite limits. These functions separately get arbitrarily large, right? So how do we get this in a form where we can, maybe possibly use L'Hopital's rule? Well, let's see. So we got 0 plus. So let's go ahead and write this as 1 over tangent. So this is 1 over tangent x minus 1 over x. Now, one of the basic things that we are able to do from algebra is if we're taking the difference between two fractions, or difference or sum, we can simplify them, or we can write this as a single fraction by using the common denominator. So let's do that. So let's write this as a single fraction. So we're going to have x approaching 0 plus, so the common denominator here will be x times the tangent of x. Multiplying the first fraction by x over x gives me an x in the numerator. Multiplying the second fraction by tangent x over tangent x gives me a tangent x in that numerator. So then the question is, what happens to this? Well, clearly, as x approaches 0, the top approaches 0 and the bottom approaches 0. So pretty remarkable that we started out here having an infinity minus infinity case, and by just doing some basic, very basic algebra, we're able to get it as a single fraction, which now converts it into 0 over 0, right? So now we can apply L'Hopital's rule. So we have the limit as x approaches 0 plus. Now when I take the derivative of the numerator, I'm going to have 1 minus, and then the derivative of tangent is secant squared, over, now at the bottom I'm going to have to use the product rule because I have a product now. So the product rule will give me tangent of x, and then plus x times secant squared x, right? Well, what happens here? Well, as x approaches 0, secant squared, right? That approaches 1, right? The secant of 0 is 1, and 1 squared is 1. So we still have 0 in the numerator, and then tangent approaches 0, and then we have 0 times 1, so the denominator approaches 0, and we have another 0 over 0 form. So what we have to do is keep differentiating, right? So let's see what happens. Another application of L'Hopital's, right? Taking the derivative of the top, so now we'll have 0, and then we'll have minus. Now, we have to use the chain rule here, so first bring the power down, keep the secant. Nope, gotta take away 1 from that. So bring the power down, keep the secant x, and then multiply by the derivative of secant, which is secant x tangent x, right? And then that's all over. Now what do we have in the bottom? So we'll have to take the derivative of tangent, which is secant squared, plus, and again we have to use our product rule. So we get secant squared, and then plus, and then x times, and again using the chain rule for this, we will have 2 secant x times secant x tangent x. Now what happens here is that as x approaches 0, secant approaches 1 and tangent approaches 0. So in the numerator we will have 0, but in the denominator we won't. In the denominator, look at what we're going to have. This approaches 1, this approaches 1, and then this term here approaches 0, right? So plus 0. So we do end up, you have to be careful with this. We have a 0 in the numerator, but we don't have a 0 in the denominator. We have 0 divided by 2, so in this case the limit comes out to be 0, right? So here is one where it's a limit as x, well, it's an indeterminate form where we have infinity minus infinity, and we end up getting 0 as that particular limit, right? Let's try another one of this form. So let's take the limit as x approaches infinity now. So let's take a limit at infinity, and the function is x minus the square root of x squared plus 4x. Okay. So if you look at these two functions, yes, the limit as x approaches infinity of x, that's positive infinity or just infinity. And then the limit as x approaches infinity of the square root of x squared plus 4x, that's also infinity. Right? So both of these functions are getting very, very large. Well, how do we handle this? Well, in this case, we don't have any trig functions to like rewrite them as a reciprocal or so forth. But what we have is we're going to actually show that we can evaluate this using our algebraic methods from way back when we did limits. And what we're going to do, because of the radical, we are going to multiply this fraction, and I say fraction because I'm going to put it with a denominator of 1. I'm going to take this fraction and multiply the top and the bottom by the quantity x plus the square root of x squared plus 4x. So that multiplies the top, and the same thing will multiply the bottom, right? So we're using that conjugate approach, right? And let's see what happens. So we have the limit as x approaches infinity. Now when I expand the top, essentially what I have in the top, in the numerator, is I have a minus b and then a plus b. So with that product, I'm going to end up with x squared minus the square root times itself. So the square root squared, which means that the root goes away, and I'm left with this. And then at the bottom, all I have is x plus root x squared plus 4x, right? So we have the limit as x approaches infinity. In the numerator, the x squared goes away, and I'm left with negative 4x over x plus the square root of x squared plus 4x. Now, it's been a while since we've done limits at infinity, but remember, this is an algebraic function. And what we have is we can look at dominant terms. So there are 3 dominant terms here. There's a single term here in the numerator. We have this term here that's not under the square root, and then we have this term here that's under the square root. So these boxes indicate dominant terms. Okay. So as x gets large, as x approaches positive infinity, what are we going to end up with? So using dominant terms, we have our negative 4x, and then at the bottom we have our x, and then plus the square root of x squared. But since x is positive, right, how do we know x is positive? Well, it's going to positive infinity, so it's definitely positive. So since x is greater than 0, the square root of x squared is equal to x, right? In fact, let me put one extra step here. In general, this is true, but because x is positive, then the absolute value of x ends up being x, right? So we can reduce this even further. So we got the limit as x approaches positive infinity, and we have negative 4x over x plus, and then this reduces to x. So what do we end up with? Well, we end up with something that can be reduced quite nicely, because in the numerator we have negative 4x, in the denominator we have a positive 2x, so this reduces to a constant term completely. So it's the limit as x approaches infinity of negative 2, and again the limit of a constant is that constant, right? So again, it just shows you we started out with this infinity minus infinity form, right? That's what we ended up with right here. That's this, our infinity minus infinity form. And here we were able to use some of our older techniques, like rationalizing, using dominant terms when we have a limit at infinity of algebraic functions. These are all important things that we have to remember. We can't forget them. And then this reduced to this nice constant term. So the limit of that function is x is negative 2. All right. So these are a few forms, the 0 times infinity and then infinity minus infinity form. There are several other forms that we will look at in the next video, and these are all, they're different, but they're all approached in a similar manner. And what I would say is these limits will involve using that change of base technique that we used earlier when we were dealing with those, we call them like those super exponential functions. We'll see similar techniques being needed for the next set, the next and final set, you might be happy to hear, of these indeterminate forms. So see you in the next video.